Welcome, architects and developers. Today we are diving into the heart of autonomous AI, cycles, and reasoning loops. We will explore why linear execution is dead and why loops are the critical engine for true AI reasoning. Let's get started. Let's define what we mean by cycles in AI. In traditional software development, and even early generative AI pipelines, we built systems using directed acyclic graphs, or DGs. Data flowed in one direction. You send a prompt, you get a response, and the program terminates. But true intelligence doesn't work that way in the real world. Complex tasks often occur in dynamic environments where solutions are not immediately apparent. Therefore, an autonomous agent operates in a continuous sense-reason-plan-act loop to pursue its goals. A cycle allows the AI to perceive its environment, form a plan, take an action, and, crucially, observe the results of that action before deciding what to do next. This cyclical architecture is the fundamental difference between a basic chatbot and an intelligent agent. Take a look at this flowchart representing the fundamental cognitive loop. Instead of a linear pipeline that ends after step 1, the agent moves from perceiving the environment into the reason and plan node. It executes an action, and the resulting observation flows right back into the reasoning engine. This feedback loop allows the agent's state and understanding to evolve organically over time, bringing us closer to true autonomous problem-solving. Why exactly are loops so critical for reasoning? Because the real world is messy. Imagine your AI is tasked with querying a database. In a linear prompt chain, if the initial API request fails due to network issues or incorrect argument formats, the application simply crashes. There is no room for recovery. However, when you implement a reasoning cycle, failure is no longer fatal. It becomes data. If a tool throws an error, that error message is fed back into the LLM during the next loop iteration. The agent can read the error, realize it used the wrong parameter, and autonomously adapt its approach. Loops provide the cognitive breathing room for an LLM to evaluate its own failures and iterate toward success, achieving massive fault tolerance in production environments. This diagram contrasts failure in a cyclic system versus a linear one. When the LLM executes the API tool, a success routes down to the final answer. But look at the error path. Instead of terminating, the error code routes to an analyze error node. The agent inspects the failure, adjusts its parameters, and loops back up to the LLM reasoner for another attempt. This self-healing architecture is only possible through cycles. How do we actually implement these cycles? Every programmer is familiar with while loops, which run until a hard-coded variable reaches a limit. But in Agentic AI, we introduce a paradigm shift, the LLM-driven loop. The key to the agent architecture is to have an LLM control the stop condition, that is, the model uses its reasoning capabilities to decide when to stop looping. We give the LLM access to external tools and explicitly instruct it to evaluate the context after every step. If the LLM realizes it needs more data, it outputs another tool call, keeping the loop alive. If the LLM determines it has fully answered the user's original query, it calls a specialized final answer tool or outputs a completion token to break the cycle. The intelligence of the system lies in the LLM acting as its own routing engine. Here we visualize the LLM-driven stop condition. The current graph state feeds into the central LLM evaluator diamond. This isn't a hard-coded if statement, it's a dynamic neural network evaluating the context. If it decides it lacks information, it routes left to invoke tool, bringing fresh data back to the state. Once its reasoning confirms the task is complete, it breaks the cycle and routes right to exit the loop. Let's deep dive into the most famous implementation of cyclic reasoning, the REACT methodology. REACT stands for Reason plus Act. It forces the LLM to structure its loop into explicit, verifiable phases. First is the thought, where the LLM externalizes its internal reasoning. Second is the action, where it invokes a tool based on that thought. Third is the observation, where the external system feeds the raw tool output back into the context window. The interleaving of reasoning and actions creates a feedback loop in which the model repeatedly cycles through this thought-action-observation process. This is profoundly important because it forces the LLM to pause its text generation and wait for factual, external data, drastically reducing the chance of hallucination. The cycle repeats continuously until the thought concludes that the final answer is ready. This flow tracks the REACT cycle. We start at thought, where the agent decides it needs data, leading to an action to call an API. The environment returns an observation. The critical juncture is the diamond. Is the task done? The agent reasons over the observation. If no, the loop restarts, generating a new thought based on the new data. If yes, it breaks out to deliver the final answer. To build these complex cycles in production, developers use LangGraph. Traditional orchestration frameworks are limited to directed acyclic graphs, DGs, meaning they physically cannot loop. LangGraph was built specifically to solve this. By combining nodes and edges, you can create intricate, looping workflows that allow the state to evolve over time. In LangGraph, you define a state object that gets passed from node to node. The magic happens using conditional edges. A conditional edge is a Python function that inspects the current state and dynamically decides where to route the execution flow next. For example, if the last message in the state contains a tool call, the conditional edge routes the flow back into the tools node, creating the cycle. If no tools are called, it routes to Yendi. LangGraph manages these cycles safely, ensuring you don't hit infinite loops by enforcing maximum recursion limits. Here is the architectural layout of a cyclic LangGraph application. Execution flows from start to the LLM node. The vital piece is the conditional edge below it. This edge inspects the LLM's output. If a tool call is detected, the flow loops backwards into the tool's execution node, which executes the code and feeds the result back into the LLM node. This loop sustains itself until the conditional edge detects a final text response and routes to Yendi. Let's cement this with a highly valuable, real-time use case, an autonomous code debugging agent. Imagine you ask an AI to write a complex Python script to calculate financial risk. In a linear system, the AI writes the code and hands it to you. If there's a syntax error, you're stuck fixing it. But if we implement a reasoning loop, the system transforms. The agent writes the code, but instead of giving it to you, it routes to a sandbox execution tool. The tool runs the code and inevitably hits a traceback error. Because of our cyclic architecture, this isn't a failure. The error is routed back to the LLM as a new observation. The LLM reads the traceback, reasons about why it failed, modifies the code, and loops back to the execution tool. It will continuously cycle writing, testing, failing, reasoning, and rewriting until the code compiles flawlessly. You receive a guaranteed working product. This diagram showcases the autonomous debugging loop. The code generation LLM creates a script and sends it to the sandbox. If the sandbox encounters a traceback error, the flow loops via the red self-correction node directly back to the LLM, providing the exact error message. The cycle iterates until the sandbox verifies the code, taking the green path to return the validated product to the user. As we conclude, we must recognize that loops unlock the highest level of agentic design, the self-correction pattern. This is a self-correction loop where an agent generates a preliminary output and then explicitly critiques it against its initial goals, leading to a much more reliable final result. You can even split this across multiple agents in an actor-critic loop. One agent drafts a financial report, and a separate critic agent reviews it for compliance. If the critic finds an error, it rejects the draft, forcing the loop to cycle back to the writer agent. This internal reasoning loop ensures that only polished, verified work ever reaches the human user. Mastering cycles, loops, and state management is the exact dividing line between amateur AI wrappers and true enterprise-grade intelligence. Thank you for joining this deep dive. To truly master these architectures, I invite you to like, subscribe, and visit quicktechie.com for premium certification prep, including extensive Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Keep building. Our final diagram illustrates the actor-critic self-correction loop. The generator agent drafts a response and passes it to the critic agent. The critic rigorously evaluates the draft. If it falls short, the workflow loops back to the generator with explicit feedback on what to fix. The system only breaks the cycle and delivers the final output when the critic approves, ensuring unparalleled enterprise quality.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by Quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks, you can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.